Hi, my name is Rachel O'Sullivan, and I'm a third-year neuroscience PhD student at UCSF. I'm really honored to be an ARC scholar, and I'm excited to share my project with you. At UCSF, I have an amazing CureBex lab, and in the CureBex lab, our goal is to delineate the neural circuits that underlie emotional behavior and how these circuits go awry in psychiatric illness. I'm particularly interested in understanding avoidance behavior, which is a characteristic feature of many anxiety disorders. The hippocampus, and specifically the VCA1 subregion, highlighted here in green, is one area of the brain that is known to promote many different forms of motivated and emotional behavior, including avoidance behavior. VCA1 is an extremely complex and heterogeneous region. It's made up of many different cell types, and it receives inputs and sends outputs to many different brain regions, as you can see highlighted here. It's currently thought that the intricacy of VCA1 circuitry is what allows the region to promote such a diversity of behavior. As shown in the schematic, the idea is that specific VCA1 cells encode specific pieces of information, and then this information is routed to different downstream areas that promote different behaviors. And there's mounting evidence that supports this hypothesis. One experiment from our lab demonstrated that in mice, if you let them roam in a two-chamber box and you stimulate VCA1 neurons that project to the lateral hypothalamic area, but you only provide the stimulation on one side of the box, animals will avoid the stimulation paired side, which you can see in the heat map at the bottom of the slide. If you do the same stimulation paradigm, but you do it on a different pathway, the VCA1 to basal amygdala pathway, animals don't show this increased avoidance behavior, suggesting that different VCA1 projections drive different behaviors. And in imaging experiments that measure fluorescent calcium indicators as a proxy for neural activity, we have found that this VCA1 to lateral hypothalamic area projection not only drives avoidance, but is also enriched in cells that preferentially fire while animals explore an anxiogenic environment. In other words, these VCA1 to lateral hypothalamic cells store a representation of an anxiogenic environment, and they do so to a significantly greater extent than VCA1 to basal amygdala cells. Building on these experiments, I want to understand a different form of avoidance behavior. I want to figure out how VCA1 represents learned cues that promote avoidance, cues that are inherently neutral but become associated with an aversive outcome, so that over time, exposure to this cue ultimately drives avoidance. To do this, we have set up a new task in lab. Animals are put into a two-chamber box. On one side of the box, a light will flash a few times prior to the delivery of a shock, and animals must learn to avoid the light in order to avoid being shocked. Where the animal is in relation to the light determines whether it must exhibit active or passive avoidance. In initial experiments, I wanted to first determine whether VCA1 had any effect on performance in this task. So I took a sledgehammer approach and used a targeted viral injection of tetanus toxin to permanently silence VCA1. And what I found was quite interesting. In these graphs, the x-axis indicates the training session. Animals went through 6 sessions and in each one received 30 active and 20 passive avoidance trials. And the y-axis indicates the percent of those trials they completed correctly. As you can see, animals with a silenced VCA1 performed better and learned faster than control animals in both active and passive avoidance trials. This opens up a lot of questions about the role VCA1 plays in the process of learned avoidance. To learn more, please come check out my poster, and thank you, ARC, so much for all of your support.